Kamath, let's do this. Journey with me as we face, overcome, and befriend the challenges ahead. We can because we are Mathemati Isinyan. I am Teacher Andrew, your soulmate. Allow me to guide you in learning the different concepts and skills in Mathematics 9. In the previous episodes, you've been hearing me say equals, equal to, is the same as, equivalent to, all of which can be written as a mathematical symbol equal sign. In today's episode and on the next one, we will be much more familiar with the use of the following symbols: is greater than, is less than, is greater than or equal to, is less than or equal to. The greater than symbol is used to mean more than, above, or exceeding. The less than symbol is used to mean smaller than or below. The greater than or equal to symbol is associated with the following: minimum, at least, more than or equal to, not below, no less than. The less than or equal to symbol is associated with the following: maximum, not to exceed, at most, no more than. Let's see what symbol we must use to represent this situation. A company plans to increase the size of the box for the packaging of their canned sardines. The length of the original packaging box is 20 inches longer than its width. The height is 12 inches, and the volume is at most 3,600 cubic inches. What could be the range of the length and of the width of the original packaging box? How do we represent the volume of the original packaging box? The volume V of the box, which is an example of a rectangular prism, is equal to the product of its length, width, and height. Length L is 20 inches longer than the width W. Hence, the equation L equals W plus 20. The height H is 12 inches. Since the dimensions of the box are all in inches, and its volume is expressed in cubic inches, we may omit the units when we represent the situation using a mathematical sentence. And so, in terms of the width W, the volume V of the box can be expressed as binomial W plus 20 times W times 12, or simply 12W times the binomial W plus 20. The volume of the box is at most 3,600 cubic inches. Which word or phrase gives us clue what symbol we must use? At most. Which symbol is this associated with? Less than or equal to? So, we express the volume of the box in symbols as 12W times the binomial W plus 20 less than or equal to 3,600. This mathematical sentence is an example of inequality. Before we get excited to multiply the quantities on the left side of the inequality, we may divide both sides of the inequality by 12. So, we will be dealing with lower constants or coefficients. When we divide or multiply both sides of an inequality by a positive number like 12, the inequality symbol remains or is not changed, unlike when we divide or multiply both sides by a negative number. The inequality symbol is changed by its opposite symbol. Thus, inequality is simplified as W times the binomial W plus 20 is less than or equal to 300. Multiplying the quantities on the left side, we have the inequality W squared plus 20w is less than or equal to 300. It must be clear now that this inequality is an example of quadratic inequality. In one variable, since the highest exponent of the variable in it is 2. A quadratic inequality in one variable is an inequality that contains polynomial whose highest exponent is 2. It can be expressed in the following forms where a, b, and c are real numbers and a is not equal to 0. So we have ax squared plus bx plus c is greater than 0. Ax squared plus bx plus c is less than 0. We also have ax squared plus bx plus c is less than or equal to 0. And ax squared plus bx plus c is greater than or equal to 0. Going back to the quadratic inequality we wrote earlier, let us express it in the form ax squared plus bx plus c is less than or equal to 0. So we apply subtraction property of inequality. We decrease both sides by 300. The resulting inequality is w squared plus 20w minus 300 is less than or equal to 0. This means that w squared plus 20w minus 300 is less than 0, or w squared plus 20w minus 300 is equal to 0. How do we solve quadratic inequalities in one variable? Here are the steps. Step 1. Solve the quadratic equation that corresponds to the given quadratic inequality. The inequality w squared plus 20w minus 300 is less than or equal to 0 corresponds to the quadratic equation w squared plus 20w minus 300 equals 0. We can solve this quadratic equation by factoring. W squared plus 20w minus 300 is equal to the product of the binomials w plus 30 and w minus 10. Hence, we have the equation w plus 30 times the binomial w minus 10 equals 0. Equating each factor to 0, we should obtain that the values of w are negative 30 and 10. So, the roots of the equation are negative 30 and 10. These will also serve as the critical points that will divide the number line into intervals. Step 2. Test the roots of the quadratic equation obtained in step 1 against the quadratic inequality to see whether they are part of the solution set. A solution set is the set of all values of the variable in the inequality for which the inequality is true. Let's express the polynomial in the quadratic inequality in its factored form, which was shown earlier in step 1. We now check if negative 30 and 10 are part of the solution set by substitution. Take note that the symbol in the inequality is less than or equal to. So, if upon substitution, the obtained value of the polynomial is either negative, which means less than 0, or exactly 0, then the root is part of the solution set. Both negative 30 and 10 make the polynomial in the inequality equal to 0. This only means that they are part of the solution set. Step 3. Plot the critical points on the number line and divide the number line into regions using these critical points. These critical points serve as the boundaries. The critical points are negative 30 and 10, which are also part of the solution set of the inequality. They are in fact the values of the variable w that make the polynomial equal to 0, and they are also the boundaries. When we plot negative 30 and 10 on the number line, we use solid circles since they are part of the solution set. Also, we are going to draw a solid line through each of these numbers. So, for the equal to 0 part of the inequality, we already obtained that negative 30 and 10 are the solutions. We have to determine now at which values of w will the polynomial in the inequality be less than 0 or negative. We expressed the polynomial as the product of two quantities, two binomials to be specific. The polynomial will yield a negative result when the values of the factors are of different signs. That is, case 1, w plus 30 is less than 0 and w minus 10 is greater than 0. Case 2, w plus 30 is greater than 0 and w minus 10 is less than 0. Hence, the solution set for the less than part of the inequality is the union of the solution sets for the case 1 and case 2. Step 4. Determine which region or interval in the number line contains the solution set of the inequality. We need to identify the sign of the value of each factor in each region or interval. We do this first for the factor w plus 30. In the region to the left of negative 30, we may use negative 40 as a test value. Negative 40 plus 30 is equal to negative 10. This means that in this region where w is less than negative 30, the value of the factor is negative. In the region between negative 30 and 10, we may use 0 as a test value. 0 plus 30 is equal to 30. This means that in this region, where negative 30 is less than w, but w is less than 10, the value of the factor is positive. In the region to the right of 10, we may use 20 as a test value. And 20 plus 30 is equal to 50. This means that in the region where w is greater than 10, the value of the factor is also positive. This time, we will check the value of the factor w minus 10 in each region. In the region to the left of negative 30, we may use negative 40 as a test value. Negative 40 minus 10 is negative 50. This means that in this region where w is less than negative 30, the value of the factor is negative. In the region between negative 30 and 10, we may use 0 as a test value. And 0 minus 10 is negative 10. This means that in this region where negative 30 is less than w, but w is less than 10, the value of the factor is also negative. In the region to the right of 10, we may use 20 as a test value. 20 minus 10 is equal to 10. This means that in the region where w is greater than 10, the value of the factor is positive. Let's see the graph once more. This would help us identify the solution set for the less than part of the inequality. Recall that we came up with two cases as to what would satisfy the less than part of the inequality. In case 1, the factor w plus 30 must be less than 0 or negative, and the factor w minus 10 must be greater than 0 or positive. To satisfy the inequality, binomial w plus 30 times binomial w minus 10 is less than 0. Looking at the graph, do we see a region where the value of the factor w plus 30 is negative and that of the factor w minus 10 is positive? The graph says no. Hence, there is no solution for case 1. We represent it using the symbol for empty set. In case 2, the factor w plus 30 must be greater than 0 or positive, and the factor w minus 10 must be less than 0 or negative to satisfy the inequality. Binomial w plus 30 times binomial w minus 10 is less than 0. Looking at the graph, do we see a region where the value of the factor w plus 30 is positive and that of the factor w minus 10 is negative? The graph says yes, it is in the region where the value of w is greater than negative 30 but is less than 10. Hence, there is a solution for case 2, given by the double inequality. Negative 30 is less than w and w is less than 10. We may write it in the interval notation, which is an open interval from negative 30 to 10. We use parentheses when the boundaries are not included in the solution set. So, the solution set for the less than part of the inequality is the union of empty set and the solution set for case 2, which is just equal to the same solution set for case 2. Let's record this in the other table. This only means that the solution to the inequality w squared plus 20w minus 300 is less than or equal to 0 can be expressed by the double inequality. Negative 30 is less than or equal to w and w is less than or equal to 10. This can also be expressed in set builder notation. W is the set of all w's, which are real numbers, such that negative 30 is less than or equal to w and w is less than or equal to 10. Using interval notation, this inequality can be written this way. We use brackets to indicate that the boundaries, which must be arranged in ascending order, are included in the solution set. The value of w is not below negative 30, but not above 10. We may graph this on a number line this way. But will all the values in this solution set be acceptable answers to the question, what could be the range of the length and of the width of the original packaging box? The length and the width of the box can't be 0 or negative. Hence, the value of the variable w, which represents the width of the box, can be expressed as 0 is less than w and w is less than or equal to 10. This means that the width is above 0 inch, but it is not longer than 10 inches. Since we represented the length as w plus 20, adding 20 to the sides of the double inequality, 0 is less than w and w is less than or equal to 10, must give us the range for the length of the box. The length is above 20 inches, but not longer than 30 inches. Kagamath, ready your pen and paper. It's Math the Moment! Let's solve this inequality. 5x squared minus 27x plus 10 is greater than or equal to 0. Now answer the following questions. Number 1. What are the roots of the quadratic equation that corresponds to the given inequality? For 30 seconds, go! Time is up. The corresponding quadratic equation is 5x squared minus 27x plus 10 equals 0. And 5x squared minus 27x plus 10 is factorable. Expressing this polynomial in factored form, the equation can be written as 5x minus 2 times the binomial x minus 5 equals 0. And equating each factor and then solving for x, we will obtain that the values of x are 2 over 5 or 2/5 and 5. And these numbers are the critical points, and hence shall divide the number line into intervals or regions. Question number 2. Are the roots 2/5 and 5 part of the solution set of the quadratic inequality? For 10 seconds, go! And time is up. The answer is yes. Let's check by substituting these in the inequality. We use the inequality in which the polynomial is expressed in factored form. The roots 2/5 and 5 are indeed part of the solution set of the inequality. They satisfy the equal to part. Question number 3. Plot the critical points on the number line. Use lines to divide the number into regions or intervals. In plotting the critical points on the number line, what kind of circles should be used? And what kind of lines should be used to draw through each of the critical points? For 15 seconds, go! And time is up. The number line should look like this. Solid circles are used and solid lines are drawn through each of the critical points. I already added the details that at x equals 2/5, the value of the factor 5x minus 2 is 0, and at x equals 5, the value of the factor x minus 5 is 0. Item number 4. We should identify the set of values of x that will satisfy the greater than part of the inequality. Guided by the factored form of the polynomial in the inequality, identify the cases in which the product of the values of the binomials is greater than 0 or positive. For 15 seconds, go! And time is up. The product of the values of the two binomials is positive, since greater than 0 simply means positive. Hence, these two values must have the same sign. There are two cases for this. Case 1, 5x minus 2 is less than 0, and x minus 5 is also less than 0, and both are negative. In case 2, 5x minus 2 is greater than 0 and x minus 5 is also greater than 0. So both are positive. Item number 5. Use a test value to identify the sign of the value of each factor in each region or interval. Then add these signs on the graph. For 1 minute, go! Time is up. See the computation. Then, we update our graph indicating the signs. For item 6, recalling case 1 in which both signs are negative and case 2 in which both signs are positive, what is the solution set of each? Write your answer in interval notation. 10 seconds, go! Time is up. For case 1, the solution set is the open interval containing the boundaries negative infinity and 2/5. For case 2, the solution set is the open interval containing the boundaries 5 and positive infinity. The union of these two sets is written this way. Expressed as inequality, the solution set is written this way. These show the same set of values of x that satisfy the greater than part of the given quadratic inequality. Let's record this in the table. For item number 7, what is the solution set for the inequality expressed as binomial 5x minus 2 times binomial x minus 5 is greater than or equal to 0? Express it as an inequality and an interval notation. 10 seconds, go! And time is up. As an inequality, the solution set is the inequality x is less than or equal to 2/5 or x is greater than or equal to 5. This denotes that, indeed, 2/5 and 5 are part of the solution set as indicated by the equal to part of the symbols. Written in interval notation, we see half-closed intervals, which are also called half-open intervals. This is read as semi-open from negative infinity to 2/5, union semi-closed from 5 to positive infinity. We use bracket beside a boundary that is included in the solution set. We always use parentheses for infinities, and the word or used in the inequality that expresses the solution set is translated as the symbol for union of sets in the interval notation. That has been another thrilling mathathon. Thank you for joining me today. Let us spread the love for math. We can because we are Mathemati Isin yan.